Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Our topic for today is aromatic hydrocarbons. Hydrocarbons are also known as arenes. Since most of them possess pleasant odor, they are called aromatic compounds. In Greek, the word aroma, meaning pleasant smelling, so they are called aromatic compounds. Most of such compounds were found to contain benzene rings, so they are called benzenoids. For example, C6H6 is benzene, toluene. Two benzene rings fused together are called naphthalene. This compound is called biphenyl. Such aromatic compounds which contain a benzene ring, these are called benzenoids. There are some other aromatic hydrocarbons which do not contain benzene ring but are aromatic in nature. They are called non-benzenoid. For example, pyrrole, furan, thiophene, pyridine, all these are non-benzenoid. They do not have benzene-like structure but they are aromatic compounds. Nomenclature and isomerism. So, when a methyl group is attached to benzene, it is called methyl benzene. In common system, it's called toluene. When two methyls are attached, then it is called 1,2-dimethyl benzene or orthoxylene when they are present at adjacent positions. When they are present at one position and three, they will be called 1,3-dimethyl benzene or metaxylene. And when they are present at 1 and 4 position, they are called 1,4-dimethyl benzene or paraxylene. So this is how they are named. This is IUPAC system, and the one in bracket is the common system of nomenclature. Structure of benzene. So benzene was observed by Michael Faraday in 1825. The molecular formula is C6H6, and this formula indicates high degree of unsaturation. And now this formula does not relate to any of the formulas of alkane, alkene and alkynes. Alkane are CnH2n plus 2. With 6 carbon atoms, the formula becomes C6H14. Here it is C6H6. Similarly, it is not similar to alkene or alkyne with 6 carbon atoms. So this indicates that the number of unsaturated bonds are high in case of benzene. Due to its unique property and unusual stability, the actual structure, it was very difficult to find the actual structure, and it took a long time to assign its structure. Now, benzene is a stable molecule, and when ozone is added to it, it forms a triozonide, which indicates that it has 3 double bonds. So when we put these double bonds in a cyclic structure of 6 carbon atoms, these double bonds come at alternate positions, double, single, double, single. But if this was to be the structure, then the double bond would have a different bond length than single bond, and there would be 2 such structures, one with double bond present between 1 and this is 2, 3, 4, 5, 6, then between 1, 6, 2, 3 and 4, 5, or between 1, 2, then 3, 4 and 5, 6, like this. where there is a single bond in previous structure, there could be a double bond, and two such structures should have come. But there is only one mono-substituted derivative, which means that this structure is equivalent to this structure, and benzene has one structure only, not two different structures. So this indicates that all 6 carbon and 6 hydrogen atoms of benzene are identical, because there is only one mono-substituted derivative, means all 6 carbon and 6 hydrogens of benzene are identical. So on the basis of this observation, Auguste Kekule in 1865 proposed that the benzene is having two structures, one with double bond in this position. And now, because the structures suggested by Kekule are having double bond here, then if it was to be a di-substituted benzene, then there would have been two isomers. But what we actually find is that there is only one structure with two bromine groups attached to adjacent position. So that then, to explain this property, Kekule suggested the concept of oscillated nature of double bonds in benzene. That is, the double bond keep migrating from their usual position to next position to again the same position. So even with this modification, Kekule's structures could fail to explain the unusual stability and preference to substitution reactions. If there are 3 double bonds, it should undergo addition reactions, but rather than addition reactions, it's preferring to have substitution reactions. But later on, we came to know the explanation for this anomaly, and we could explain the structures with the help of resonance. So let us take the help of resonance and discuss the stability of benzene. According to valence bond theory, we can now explain the concept of oscillating double bond in benzene. So this is explained by resonance. Benzene is a hybrid of various resonating structures, of which 2 are the major structures which contribute most to the resonance. One is having double bond in these positions, and the other one in the next positions, that is these positions. And actual structure is a hybrid, is an average of the 2 resonating structures, which is known as resonance hybrid, where we show the pi electrons of the 3 double bonds in form of a dotted circle or a complete circle, suggesting that the electrons are migrating all over the 6 carbon atoms of the benzene structure. This hybrid structure is represented by inserting a dotted circle or a circle in the center of a hexagon. The circle represents the 6 electrons of the 3 double bonds which are delocalized on all the 6 carbon atoms of the benzene ring. The orbital structure will also give us a picture of the structure of benzene. So in benzene, the carbon atom is sp2 hybridized, and of the 3 sp2 hybrid orbitals, 2 are engaged in sigma bond with the adjacent carbon atoms, and the third one is engaged in a sigma bond with the 1s orbital of the hydrogen atom. So there are in all 12 sigma bonds. So this is the sigma bond picture. Now we also have one unhybridized p orbital on each of the carbon atom. Now these can overlap sidewise to form a pi bond. If this carbon atom number 1 and 2 are overlapping, and then 3 and 4 and 5 and 6 are overlapping, then the structure could be represented by this structure. On the other hand, if instead of 1 and 2, 2 and 3 are forming bond, and then 4 and 5 and then 5 and 6, then we can represent this structure with this diagram. So double bonds are either present between 1 and 6, 2 and 3 and 4 and 5, or between 1 and 2, 3 and 4 and 5 and 6. So these are the 2 possibilities, and the 2 possibilities are equal possibilities. So if the double bond structure was this one, then this bond length should have come out to be greater than the double bond length. So these two bond lengths should be different. But X-ray diffraction studies show that these bond lengths are equal. So, and the internuclear distance is same. So if the internuclear distance is same, then there is equal probability for the p orbital of each carbon atom to overlap with the p orbital of adjacent carbon atom. It can overlap with this carbon atom as well as with this. So what X-ray diffraction studies suggest, it can be explained if we say that the 6 pi electrons are delocalized and can move freely about the 6 carbon nuclei instead of 2, like this. These pi electrons are not only moving between these two carbon atoms but also over the rest of the carbon atoms also. So the pi electron cloud is above and below the hexagonal structure. So this suggests that the stability will be more when all the pi electrons are moving simultaneously on all the 6 carbon atoms. Then in that case, the delocalized pi electron cloud is attracted more strongly by the nuclei of carbon atoms and than the electron cloud localized between 2 carbon atoms, and therefore presence of delocalized pi electron in benzene with it moving on all the 6 carbon atoms will make it more stable than the hypothetical bond structure where the pi electron cloud is moving only between 2 carbon atoms. X-ray diffraction studies also reveal that benzene is a planar molecule. Had any one of the above structures of benzene been correct, then we would have found 2 types of carbon-carbon bond lengths, one double and one single. But X-ray studies show that all are same carbon-carbon bond lengths, which are average of the double and single. That is, a double bond is 133 picometer and single bond is 154, but actual bond length comes in between the two. So we see that the bond is actually not purely double bond, it is in between double and single. So absence of a pure double bond, it will explain why the benzene does not undergo addition reactions and undergo substitution reactions, thereby delocalizing the pi electron cloud on all the 6 carbon atoms, and which can be rightly shown by this resonance hybrid of benzene. As aromaticity, benzene was considered as parent aromatic compound, though all other aromatic compounds were thought to be derived from this parents. For example, if Cl is attached to benzene, it's chlorobenzene. If CH3 is attached, then it is methyl benzene. If OH is attached to benzene, it is phenol. But now we know that apart from benzene-like structures, we also have structures where there is no ring system. That is, even those compounds are aromatic which do not contain benzene ring. For example, pyrrole, furan, thiophene, pyridine. These are also aromatic compounds. So they will be called non-benzenoid, whereas those which are derived from benzene rings are called benzenoids. So aromatic compounds can be said to be divided into 2 classes, benzenoids and non-benzenoids. Now, any ring system which is showing aromaticity may or may not have benzene ring, but it should possess the following characteristics. Planarity, it should be planar. The pi electron cloud should be completely delocalized in the ring, and the compound should obey a 4n plus 2 pi electron rule, which is called Huckel's rule. So the number of pi electrons should be 4n plus 2, where n can be 0, 1, 2. For example, in benzene, the value of n is 1. So 4 into 1 plus 2, 4 plus 2, 6. So it has 6 pi electrons. Similarly, cyclopentadienyl anion also has 6 pi electrons moving all over the compound. Similarly, cycloheptatrienyl cation also has 6y electrons. So because they are obeying Huckel's rule, all these compounds are aromatic in nature. Similarly, naphthalene has 10 pi electrons. It is also obeying Huckel's rule, where the value of N is 2. Similarly, anthracene and phenanthrene are also aromatic compounds with N is equal to 3 and 14 pi electrons, and these structures obeying the Huckel's rule, aromaticity rule. Preparation of benzene. Benzene is commercially isolated from coal tar. However, it may be prepared in the laboratory from the following methods. Number 1, cyclic polymerization of ethyne, acetylene. So when acetylene is heated in a red hot iron tube to a temperature of 873 Kelvin, it undergoes cyclic polymerization to form benzene. Then next method is decarboxylation of aromatic acids. When sodium salt of benzoic acid is heated with soda lime, a 3:1 mixture of sodium hydroxide and calcium oxide, the sodium carbonate is removed and hydrogen is added to form benzene. So benzene is formed. The vapors of phenol are passed over heated zinc dust. Then also O gets removed with zinc as zinc oxide and benzene is formed. Properties of aromatic compounds. Physical properties. Aromatic hydrocarbons are non-polar molecules and usually colorless liquids or solids with characteristic aroma. Naphthalene ball, an aromatic compound, is used in toilets and preservation of clothes because of its unique smell and moth repellent property. Aromatic hydrocarbons are immiscible with water but readily soluble or miscible in organic solvents. They burn with a sooty flame. Chemical properties. Arenes are characterized by electrophilic substitution reactions. However, under certain conditions, they may go addition reactions and oxidation reactions also. Electrophilic substitution reaction. The hydrogen of the benzene ring can be substituted with some electrophile such as nitro group, sulfonic acid group, halogen group, alkyl group, acyl group, etc. So let us do these electrophilic substitution reactions. So when benzene is heated with a mixture of concentrated nitric acid and sulfuric acid at a temperature of 323 to 333 Kelvin, the nitro group gets attached. Nitric acid, the H of benzene will combine with OH of nitric acid to form water, and NO2 group gets attached, so nitrobenzene is formed. Similarly, arenes, when react with halogens in presence of a Lewis acid such as FeCl3, FeBr3 or AlCl3, the H will combine with Cl to form HCl and Cl gets attached in its place, so chlorobenzene and HCl are formed. Similarly, when benzene is heated with sulfuric acid and sulfur trioxide, that is oleum, fuming sulfuric acid, the OH of sulfuric acid will combine with the H of benzene to form water, and sulfonic acid group gets attached. SO3H is attached. So this is benzene sulfonic acid. Friedel-Crafts alkylation reaction. When benzene or aromatic compounds are treated with methyl chloride in presence of anhydrous aluminum chloride, the H of benzene will combine with the Cl to form HCl, and CH3 group gets attached in the place of hydrogen to form methyl benzene, similarly ethyl benzene. The acylation reaction also can be carried out. For this, we heat the aromatic compound with acyl chloride, acetyl chloride in presence of anhydrous aluminum chloride. Again, the H will combine with the Cl to form HCl, and COCH3 gets attached to form acetophenol. Similarly, acetic anhydride will also result in formation of acetophenone. If excess of electrophilic reagent is used, then in that case, all the hydrogens can be substituted. For example, when we treat benzene with chlorine in presence of anhydrous aluminum chloride in cold condition, hexachlorobenzene is formed. The formula is C6Cl6. Addition reactions. Under vigorous conditions at high temperature, we can break the 3 double bonds and add hydrogenate to form cyclohexane, C6H12. Under ultraviolet light, 3 chlorine molecules add to benzene to produce benzene hexachloride, C6H6Cl6, which is also called gamma hexane. So there is no double bond here. All 3 double bonds break and Cl is attached to the bonds to form C6H6. There are 6 hydrogens also and 6 chlorine also, and Cl6. Combustion. When heated in air, benzene will burn to form carbon dioxide and water. So that's all in today's video. If you like the video, please do share and subscribe. Thank you. Have a nice day.